Dear students, today I am going to start with the second part of traffic engineering. Most probably you have gone through the video on the traffic engineering part 1. There I have ended up with the definition of grade of service and some numerical problem based on GOS. GOS is defined from the satisfaction of subscriber. That means you are trying to get a connection, and sometimes you may be successful and sometimes you may not be successful. So you will say that the system telecommunication company or service provider is good if all the time throughout the day you are getting opportunity to complete your call. Okay, and if you are not able to do that, you will be disgusted about the system and say that the service of the company is poor. Now, blocking probability is another parameter which is defined from exchange point of view. Okay, so as written, blocking probability is that GOS is a measure from subscriber point of view, whereas blocking probability is a measure from network or switching point of view. And you know, GOS is calculated from the number of calls rejected, and whereas the service provider will see what is the probability that the total system is busy, so that no call or no service can be provided to others. So blocking probability B is defined as the probability that all the servers in a system are busy. Now, in order to find or understand the blocking probability, we need to know the congestion theory. So congestion theory deals with the probability that the offered traffic load exceeds some value. You have 50 lines exchange. If you find that throughout the day all 50 lines are busy, so there is a probability it may happen or may not happen. So you should know this parameter. Okay. Thus, during congestion, no new calls can be accepted. There are two ways to specify congestion. Number one, there are time congestion and call congestion. Time congestion is from the point of view of the exchange, and call congestion from the point of view of the subscriber. Okay. The time congestion is the percentage of time that all servers in a group are busy, or the exchange is totally busy throughout the day. The call or demand congestion is the proportion of call arising that do not find free server. That means some calls originated are lost. In general, GOS is called call congestion or loss probability, and blocking probability is called the time congestion. You just note this point because I have seen some multiple choice question based on this fact. Okay. If the number of sources is equal to the number of servers, number of subscribers is equal to the number of lines in an exchange, then the time congestion is infinite. So it is totally occupied over throughout the day. But the call congestion is zero because everyone is getting a facility to complete their call. When the number of sources is large, number of subscribers is large compared to the number of lines in exchange, then the call congestion is equal to time congestion. Okay. So in order to find this blocking probability, we need to develop or we need to follow a certain model, mathematical model. This model is known as Markov chain. You need not be worried about the mathematical intricacy of this Markov chain process, but we are going to use this process in a very basic state. See, in order to understand Markov process, we just remember how counter counts. In digital electronics, we have studied counter, how a digital counter counts. If a clock pulse arrives, it starts from 0, it will move to 1, then 1 to 2, 2 to 3. If it is a decade counter, it will go up to 9, and again it will come back to 0. So 0 is a particular state, then 1 is another state, 2 is another state, 3, 4, 5 up to 9. So there are total 10 states. So similar to this, at a particular instant, say at the very morning, a particular call is arrived, so it is in a particular state, or there is no call is under process, so it is also a state. One call may arrive, so it will move to a particular state, and after that this call will be completed, it will go back to original state. So it may happen or may not happen. In the meantime, another call may originate, so it will move to another state, and there two calls are in progress. In this way, there may be it may come back to original state if a call is completed, or it move forward with one state to another. So this is the concept. Now this model is called birth and death process. Birth means call arriving, death means call completion. Let nt be a random variable specifying the size of the population at time t. Nt number of calls in progress. For complete description of birth and death process, we assume nt is in a state k at time t has the following properties. Pk is the probability at state k, and pk plus 1 is the probability at state k plus 1. Just like counter, state k plus 1, it may be 0, 1, 2, 3, like that. The probability of transition from k to state k plus 1 in short duration delta t is lambda k into delta t. Lambda is the arrival rate multiplied by its state into time. Okay, well, lambda k is called the birth rate in state k. The probability of transition from k to minus k 1 in the time interval delta t is mu k into delta t. Mu is called the death rate, call completion rate in state k. So based on the above properties, the birth and death process can be represented by this figure. So this is called Markov process. So 0, this state, no call are in progress. So one call arrives, so it is in state 1, another call arrive, state 2, so on. And similarly, at state 1, there may this call may get completed, so it will go back to this state. Similarly, there is another state here, so if call completed, then it will be back to this state, otherwise it will forward. So there will be randomly forward and reverse movement are there. This is the model. So this may be new to you, but this is an interesting scenario to model the practical situation. Okay, so this state transition diagram, this is called state transition diagram. State are designated by 0, 1, 2, k plus 1, so on. The probability P0, P1, Pn are called the state probabilities. The probability that no calls are in progress, P0. One call in progress, P1, so on. Under equilibrium condition, so call arriving, call getting completed. So there may be one equilibrium when arrival rate and death rate are birth rate and death rate, they may be same. Okay, so we assume that here at this position at this intermediate position, this equilibrium is achieved. So with respect to this boundary, flow rate into the boundary is probability from this state to the probability of this state multiplied with the probability of this one. So the rate of flow from here to higher state, and flow rate out of boundary, so from here to here, it is mu k probability, that is the death rate at this state, and pk is the probability of this particular state. At equilibrium, mu k pk equals to lambda k minus 1 to pk minus 1. From here, I need to find out pk, that is the state probability, okay, of the state probability of k. So we can write here, if you substitute k equals to 1, 2, 3, 4, 5, so it will be pk will be lambda 0. From here, if you substitute 1 p0, then it will be k equals to 1 p0 and so on. So lambda 0, lambda 1, lambda k minus 1 by mu 1, mu 2, mu k, and so on. So this is equation number 1. So based on this model, you can expect a question, proof of Erlang-B formula. Okay, congestion or blocking probability. What is the formula? You have to prove the formula for blocking probability. The probability that all the servers are busy. So we further simplify. There are several assumptions based on this process, Markov process, but we assume a simplification: lost call cleared. That means if call attempt is not successful, it is not clear, it is cleared. Or there is another option is that you may be in queue. Once a particular line becomes free, you will get option according to your priority or according to a queue. So you may be in queue, but here we assume if the call is if the exchange is busy, so that call will be lost, so you will not be entertained. So this is called lost call clear. Lost call clear model assumes that subscriber who does not avail the service hang up the call. So you may try once or twice, but if you do not get time, if you get annoyed with this, or you may be busy with some other job, you may not attempt further. This tries, okay. The next attempt is assumed to be a new call. So second time when he is calling in this system is considered to be a new call. It is not that the second attempt, third attempt, fourth attempt. Every time he make a call, whether it is successful or unsuccessful, it is arrival of call. Hence the call is said to be cleared. This also referred to as blocked call lost assumption. Okay, this is important. The Erlang developed this formula. According to his, the loss system can be modeled by birth and death process, with birth and death rate are as given below. Lambda k, that is birth rate, equals to lambda when k is greater than n. Number of calls arrival is more than number of subscriber line. Mu k death process equals to k into mu, k equals to this one. This is the assumption. Okay. Now if you substitute these two values in equation 1, you will have this expression. So from here, probability 0 is determined by the normalization condition. So sum of all probabilities, sum of P0, P1, P2, 3, all this will be equals to 1. That is the basic probability theory. So if you sum all these things, you will get this expression. From here, P0 is equals to this. Now once you get P0 equals to this, you substitute the value of P0 from here to the value of Pk. So you will get this one. It will be a k by k factorial, summation of k equals to 0 to n, ak by k factorial. Okay, this formula is known as Erlang B formula. There is another formula which is called Erlang C formula, which is suppose if you are put in a queue, in that case, what is the call completion rate? So that will be given by this. I shall come to this later on. Before that, let us see some example. Suppose consider a trunk group with an offered load of 4.5 Erlang and a blocking probability of 0.01. If the offered traffic increase to 13 Erlang, to keep the same blocking probability, find the number of trunks needed. Okay, A equals to 4.5, B equals to 0.01. So this figure I haven't shown. So if A and B are this thing, then you can find out, if you from here substitute, what will be the value of n from this formula. A and B are given. Okay, A and B are given. So then you have to find out the value of n. This can be calculated. Then number of trunks can be calculated as 10. Now if it is increased to 13, then forget about this one. Then number of trunks required will be 21 for the same B 0.01. Hence B 10 4.5 will be this will be 0.1. The trunk occupancy is calculated as it is A dashed, that is A equals to occupancy, one means 1 minus B n minus n. Okay, why n 1 minus B? This is the blocking probability. Then this part is the number of the probability it is blocked. Then 1 minus this is occupied, so it is providing service. So A into 1 B n minus 1 by n. So it is equals to 4.5. New value of this, it will be n equals to 10, A equals to 4.5, you can find out. And for n equals to 21, this will be this one. Okay, so for your exam, suppose n is given, A is given, you can find out trunk occupancy using this formula. Okay, let's come to this problem. A group of 7 trunks is offering 4 Erlang of traffic. Find A, the grade of service; B, the probability that only one trunk is busy; the probability that only one trunk is free; and probability that at least one trunk is free. So n is 7, A equals to 4 Erlang. Equation 4.54, that is equals to this one. This formula. B74 equals to, see this formula, A to the power n. A is given in Erlang, so it is A equals to 4 to the power 7 factorial, and this one you can calculate the grade of that is grade of service, that is equals to blocking probability. Why this is so? Because initially I mentioned, when the number of subscriber is larger as compared to the number of server, then GOS is equals to blocking probability. That's why this happens. Blocking probability that only one trunk is busy, we know PK. So say P1, only one trunk is busy, equals to AK. From here, if you substitute P1, you can find out this one. And you go through this one, you will be able to work out this problem. But following this formula, you try to solve that is based on this Erlang B formula, you try to solve the blocking probability or grade of service. What I have seen, most of the problem in based on this traffic engineering are on this formula. So please remember this formula, and you just try to remember the significance, how the blocking probability and GOS are related. What is the significance of each turn? A is the offered traffic, and what is K? K is varying number of calls arriving, and N is the total number of lines in the exchange, so on and so forth. Okay, so try to solve problems, and I'll give certain assignment and solve problems based on this formula. Okay, thank you for today.